the papillary vessels are also, this is papillary vessels, you see?
In the dermis.
So here you have the dermis, papillary vessel, epidermis here, dermis here. It's surprising to see that all these papillary vessels have almost the same profile, the same shape, but all of them are different. All of them. And they are moving. Look, they move.
Which is
so
they don't break. I mean, you want that. So what I was saying, parallel to that, you should have a whole lymphatic network, just parallel to those papillary.
Oh, certainly, certainly. And you can observe at the surface of the skin, you can observe the pulsation of all these vessels. Look here, you can observe the pulsation from the surface of the skin.
Amazing. And so we don't even, those are artery for sure. There's no vein there.
Well, this is another problem.
Yeah.
We will see around the cells, it's surprising.
Yeah.
When you look, you observe only arteries. But I think it's wrong. But the observation say it's only red. It's not blue, it's red. But we can go on for the dermis. At the surface of the dermis, you can see shapes, almost like the surface of the epidermis.
So that's not from you, right? That's electronic microscope, the dermis?
Yes, this is the surface of the dermis. It's very various. It's not always the same way of organization for the fibers of the dermis. Sometimes it's very standard, like that. Sometimes it's very parallel. But inside the dermis, you have almost only fibers. Inside the epidermis, you have always almost cells and some fibers. So the question now is, how is it with the fatty tissue hypodermis? So we have been, the epidermis is made of cells and fibers. The dermis is made of fibers and few cells. We have seen papillary vessels. This is the hypodermis. When you cut the skin, very quickly you can observe fatty lobules. And this is a section. White is fibrillar.
Fibrillar, so white is more fibrillar. And have you seen brown fat sometime?
Not very often. You have different colors for the fat. We will see that later. And this is epidermis, dermis, papillary vessels here, and this is the fatty tissue. So there is a total continuity.
Yeah.
Papillary vessels and melanocyte here.
Oh, finally, yeah.
This is the surface of the skin here, and you can see melanocyte.
And we couldn't see them before at the junction between dermis and epidermis, maybe because of the light is so strong, maybe we blur the colors, or
depend on the patient also.
The patient, okay. Yeah, if they went from, he came back from vacation or not.
If you go deeper, inside the fatty tissue, the hypodermis, sometimes you can see a high densification of fibers. This is the fascia superficialis. Here, you can observe the fascia superficialis.
And that's not scar tissue. It's not scarred. Everybody has that.
Yes, absolutely. It's inside the hypodermis. It's very useful for the surgeon because you can use it for the stitch, you know. But for example, at the level of the face, you can't find fascia superficialis. It's not an anatomical constant. And inside the fatty tissue, we are now inside the fatty tissue, inside the hypodermis, we can see fatty lobules here.
How much fat layer we have in the hand? Because you are such a hand specialist. How much fat in the hand? Usually we describe not much fat in the hand.
No. Here we are, well, depend, because I did a lot of surgery for forearm, arm, legs, and so on. So it's the same everywhere. I am not only a hand surgeon, I was a general surgeon.
All right, but do you find fat in the hand? There's much fat?
Yes, you can, but it's not really, no, in the end, you can find small muscles, you can find arteries, you can find tendon, but you can find also sometimes fat, yes.
And then, but so you have a fascia superficialis in the hand? It goes all the way there?
No, not at all.
No.
Not at all. Not at all.
Same with the foot. You don't have dorsum of the foot. There's no fat.
No, there are only skin and muscle.
No.
So here you can find fatty lobules here. And between the fatty lobules, you can find all these fibers. You could say, well, it's connective tissue. You could say that. It seems to be very logical to say that. So we observe. And look.
Wow.
All the fibers are penetrating inside the fatty tissue, the fatty lobules. It's not only a connective tissue, because it's penetrating inside. All these fibers are belonging to the fatty lobules. There is no free plane or a weak link between the so-called connective tissue and the fatty cells. No, it's a total continuity.
And you could see that those fibers don't go intercellular, but intra. They really go inside the cell. They don't go just on compartment bonds.
At the beginning, I observed that.
Yeah.
My observation was, well, I am looking some fibers going inside the fatty lobule. So what happened, really? So I tried to observe what happened for a fiber. So you see, the connection, it's a very strong connection. It's not nothing. You can observe here fatty cells. They move. It's surprising. All of them are moving together. And you can observe a fiber. Here, for example, you have a fiber penetrating inside and disappearing inside the fatty, between the cells. So the link between these fibers and all the cells here is total. So it's not a connective. It's not only connective. It's constitutive. It participates to the shaping of the fatty lobule. So it was the beginning of our experience. And so we go on. Here we are at the level between the fatty lobules and the aponeurosis. This is the area just above the aponeurosis. This is a sliding area. That means that when you move the skin, you know, when you move the skin, you use this area. And in this area of sliding, you have fibers and very few cells. But concerning the colors, you spoke about the color. All the fatty lobules are different, all of them.
It's amazing, huh? Yeah, everything is different. Like
yes,
human beings on the planet are different, all the fingerprints.
Absolutely, Bruno.
Yeah.
Absolutely. Everything is different. And this is the main observation.
So I see I see one vessel in the middle of the desert. I don't see like a nice network of vessels trying to go to every cell. It's really one vessel that you see here and there, unless they come from the other side, you know.
Well, concerning the vessels and the cells, do you want to see some, do you want to see now?
You want? Yeah, let's see some vessels. Yeah, why not? Because I imagine some cells going to be vascularized and some much less. I mean, how, if you know.
Well, yes, we can do it. So now we are speaking about vessels and cells, okay? So when you are using an endoscope, we have seen that we have observed many fibers. But it's not a world of only fibers. We have cells, we know that. But what are the links? What are the links between cells and fibers? So, what are the relationship between cells and the network? Look here. Look, all the cells are in connection with the fibers. All of them. You see the fibers? They penetrate inside the fatty lobules. Inside all this organization made of cells.
But again, we don't see too many vessels. And this is a little, those are the bluish.
Yes, we don't see the vessels. We will see some vessels.
Yeah.
Here, look here.
Okay, but you can imagine that some cells are very far from any of those vessels, and some cells are very close to it.
Yes, but don't forget that we are observing this living matter with the tourniquet on.
Yeah, you have the tourniquet, so you have a lot less blood.
Yes, and otherwise,
it would be bleeding.
It's impossible to make any movie, any film, if you have the bleeding. It's impossible. So, but look here, the cells are surrounded by vessels.
So with the tourniquet, you have venous stagnation of vein, theoretically.
Well, it depends, because sometimes you can open gently the tourniquet. And yes, sometimes you can do that. If you have time to, if you have the permission of the anesthesiologist, you can do that. But here, for example,
we don't see a vascular arteriovenous bundle. We don't see an artery, one color, and a vein of the other color next to it.
No.
You never see a vein. It's amazing, especially with a tourniquet. With a tiny bit of stagnation, you expect something even less oxygenated somehow, but and different color. But yeah.
Look here, you have cells on one side here, and here no cells. So in some place, in many places, I can say, you have no cells. So the cells are not the only responsible of the form of a body. Because in some parts, you have no cells. And even that, you have a shape and form.
A sheet of fibers. That's
Yes.
a sheet of fiber on,
Yes.
on the left.
Because fibers are everywhere.
Homo
So,
fibroticus. Homo facile.
yes. So look, we have cells here. And here, no cells at all. And look the link between the cells here and the fibers. Look. There is a total continuity. There is no
Separation, plan.
separation. There is no free plane. No, it's a total link. All these fibers are, of course, tiny fibers, but they influence the shape of the cells. Look here, you have two cells. We are going to move around the cells, and they are going to change the shape slowly. So we observe these two cells. It's like an olive, you see here. And little by little, it's going to be round. They change. The shape of the cells is changing under the influence of the fibers.
And we know in embryo, changing in pressure around the cell is going to create differentiation between a liver cell, a muscle cell, a tendon. This pressure
Yes.
will change completely the physiology, is going to change the genetic expression.
Absolutely, absolutely. And you are opening a new window, Bruno. So another example. Look, the moving of the cells under a gentle pressure. You have the vessels.
Those cells are more cuboid or are more square? Okay, that's...
Well, in fact, we think that the cells are hexagonal, but it's not the case.
Yeah, they are not. Yeah, they look like...
No, not at all. Not at all. They can change. You see here, they are completely packed, and they can change very quickly in another shape. Here, for example, you have it's not a fatty lobule. It's made of fibrocyte. So
those cells are fibrocytes?
Yes.
Fibrocyte? And so you can assume that you have collateral vessels going on the side of this main, and
here, in this example, you have only one main vessel.
And it's not because you compress and there's no blood coming. It's just that's the way it is. Some cells are far away, and some cells
Sometimes. In one of my movies, I have shown that. Sometimes you're observing cells, and you don't see vessels. But if you move gently around, just beside, and then you come back, you can see the vessels. Depend of the pressure. And I read a paper that the vascularization around the cells is not permanent.
Wow, it changed, reorganized.
They describe some cycles. Wow. Timing, a sort of timing, cycles, but it's not permanent. In this case, here, you can see main vessels with red cells here. And we can see some movement inside the cells.
And Jean Claude, I'm amazed with our fibroblasts. They describe elongated shape. Those are almost the same shape than the adipocytes and the other cells.
Yes, Bruno. Yes, you are right. It's for me, after 15 years of experience, I can say almost sure that this is an adipocyte. But that's all. That's all.
You say fibrocyte. You said fibrocyte.
Here you have fibrocyte. But when an adipocyte is more yellow. Okay. More yellow.
And those are more transparent.
Yes. Here they are very transparent. So if you look to the cells here, they move. It's not a big movement. So you have movement between cells. You observe they change the form. You have an influence of the fibers on the shape of the cells. And here, this is again fibrocyte and arteries. And look here.
Now you have a nice distribution here, exactly. I was expecting a little bit more of this. Sometimes you see vessels on their own. There's nothing like that. This is what we see in the book.
Yes.
Okay.
But there is no vein. Where is the vein? We can think that the red is the artery. So sometimes you can find what we have seen just now. That means an artery around the cell. Sometimes. But it's not always the same way. Sometimes it's less. For example, here you have arteries, but here, for example, you have an artery, but there is no apparently blood supply. But what is surprising here, you can look, is all the cells are different.
Yeah.
Look, this one, bigger than this one.
Just like a
different of this one. All the cells are different.
So we shouldn't build city with the same buildings, one next to the other, to reproduce biology. We shouldn't have cars all the same in the parking lot.
And so, in some place, like here, you have adipocyte. These are adipocyte. You know, it's yellow.
Yeah.
But you can't find any vessel.
Every book shows an adipocyte so round, so nice. And here you can see more angle than usual, even.
Yeah, look, this is like you have adipocyte, totally adipocyte. All of them are adipocyte. And wow. Look here, you have cells around the vein.
So we can say, if we look at all those pictures, we can say we have always continuity, always a signature. Every cells are different, creating a very specific signature for everybody and for every tissue. It's everywhere with the same we never have the same, like we see on book, the same cell that, I wonder even epithelium is the same. I assume all the cells will be, they are never exactly the same cloned cell that reproduce next to each other.
Yeah.
We have a really very specific cells, and they're all different. They all have a very beautiful architecture.
Yes.
All
Yes.
continuity, and all connected with fibers all around.
Yeah. So it's really a new world.
Because, we have 60, I mean, probably at our age, we're 55% water. But that give its mobility. I mean, it's like a fish or something like that. It's very fluid, so we can adjust.
Yes, it's like almost like in a fluid. And something also surprising. Here you have thousands of cells here around a vein. You see cells, cells here. Everywhere you have cells. Everywhere. Thousands and thousands and thousands. So with my endoscope, I am observing all these cells.
Wow, it's beautiful.
And look here. I am observing the cells. A fiber here, cells here. And suddenly, look what I see. Cells just beside the others.
And that's not a pericyte. Those are just little cells. It's too small, right?
Yes, but they are not in the main group.
Yeah, they're all separated. A little colony on the side, yeah.
Yes, they are separate. And the question is, are these cells in this situation from the beginning? Or are these cells migrating?
They're in exile. They've been rebel.
I don't know. So it was with this sequence, I decide to observe cells because it was surprising. I was maybe observing migration of cells. So I decided to observe cells, and it was not the only surprise. So we observe cells beside, which seem to be isolated.
Wow.
All the cells love vessels. Here, no vessels, no cells. Here, one vessel, many vessels, a lot of cells. They love vessels. They love. One vessel, you can find cells. No vessels, nothing. So there is an attraction for blood supply. Sometimes you can find cells, look here, on the surface of the aponeurotic. Sometimes you can find cells inside the muscle, inside. But these cells are not muscular cells. They are certainly fibrocyte or fibroblast, but they are not muscular cells. So inside the muscle, you have different types of cells.
What about immune cells? Could it be some macrophage or some lymphocytes or some?
I don't know.
Yeah.
I don't know. I don't know. But you have this kind of cells here, and they use the fibers. They use the fibers. Look here now. I am observing this fiber with my endoscope. I go on the right, and then this. Two cells. Alone.
That could be an immune cells now, like this, because there's no reason to have two cells without the tissue. But if you have, you know, a macrophage getting out of a, you know, monocyte macrophage, you know, or Langerhans cells, depending where you are, that will
Yes,
that will
but
make sense to have one, you know, waiting for invaders somewhere there, but out so far from
yes,
it. Yeah.
yes, you can imagine many kinds of cells, but these two cells are along the fiber, totally adherent, and only two cells. And so I decide to make many observations on cells. This example, you have a fiber and cells again. Two cells. Again, many cells along a fiber. Many cells. Again, this is a fiber. And the fiber is totally colonized by cells. Totally. And it's a fiber, you see.
Yeah.
There is a
Well,
division.
you know, we don't, oh, see, we were looking for lymphatic vessels together, and they look like this. We don't know if it's really a fiber, a vessel. We're never sure, right?
Ah, no. When
Or
it's
nerve, unless it could be a nerve. Could you, at this point, you couldn't say the difference, could you? Yeah, those fibers are a little bit more whitish, you know, milky. You are sure they are fibers. They could be nerve. They couldn't be empty vessel with no blood because of the surgery.
Here it's a fiber.
For sure. Okay.
Here it's a fiber. It's not a nerve because it's not the same. You say luminescence.
Yeah, yeah, luminosity.
Luminosity, yes. It's transparent, and it was a nerve. It will not be the same.
Okay.
So, and here, for example, you have a look here. It's almost a fatty lobule. And look, it's changing of shape all the time, but it's a fiber, completely colonized by cells, like here.
You almost feel like the cells, some cells are inside more than.
They go inside. The fibers are going inside the fatty lobule, totally inside. So I decide to go closer, and to try to have a good image of this kind of a relationship, which seemed to be in total continuity. And look here.
Wow. So do you have a picture showing really that it pull inside the cells, really for sure inside?
Look here, Bruno. You have the fiber here.
Yeah.
The fiber is penetrating inside and disappearing.
Yeah, but you cannot say if it's intercellular or intra. Can you really see it putting in the contents inside a cell?
Well, for me, it's difficult with my endoscope to prove that the fiber is going inside, because I can't with my endoscope.
We know with histology that it goes through
the fiber, which is here. Sorry.
Wow.
The fiber is disappearing inside the cluster of cells. So it's a world. I think, look here, look here. The fiber, maybe a vessel here, and cells around.
That's the difference between dead, dehydrated tissue like that, and living tissue. Exactly.
We have tried to analyze this kind of cells, and these cells have a lot of mitochondria and are secreting a lot of collagen. This is collagen, tropocollagen. Here.
Excreted by the cell. So that's a fibroblast.
Yes, it's certainly a fibroblast. Yes, this is a nucleus, and this is mitochondria.
Yeah, in gray. Yeah. So those are pre-elastic fibers, tropocollagen, pre-collagen fibers. Tropocollagen getting its helix together and creating the collagen fibers. Yeah.
Certainly.
Beautiful, yeah. It has to be fibroblast. There's no other cell that secrete that. It's beautiful, yeah. All right. I loved it. So we came back from living and to the dead matter. We did all our histology on picture like this. We have to redo everything with adding all the information from living tissue. It's absolutely amazing. Would you like to say something to conclude, Jean-Claude? How the future, for the future with all this information?
Well, concerning the future, I think that we have a lot of work to do. And it's what I call the post-Vessalian anatomy. That means not only observation, but living observation of the body. And thanks to that, you can have a way of thinking human living matter, animal living matter in a different way. I mean that we are under, as said Darcy Thompson, our living matter is under the basic physical forces of the universe. We are not a part. We are not out of this influence. We are a natural product. And we are made of natural elements under the rule of the natural physics. So another way of thinking human is possible. It's not possible now, I think, with this new technology. It's not possible to understand human living matter only with the Vesalius message and only with histology, which is made under a microscope out of the living without any color and only on 2 dimensions of space.
And dry, dehydrated. It looks like we need more concept because you see, we talk about fractal, we talk about hologram, we talk about tensegrity, we talk about chaos theory, we talk about quantum. I mean, those concepts, there's so many things we could not understand with those pictures. It looks like we need almost a more theoretical background, to be able to understand those concepts, all those things. We don't have words for everything we see here. I mean, we don't have fractal, we don't have chaos theory, we don't have tensegrity. We'll miss so much. I think we miss a lot because we don't have the concept we need to have to explain this.
Yes, I think so, Bruno. I think that we have to introduce a new way of thinking living matter. I hope that new technology, I mean endoscope with a magnification around 100, 200.
That would be amazing.
Will bring new information.
Yeah.
New information. But to do that, you have to influence new generation of surgeons to make research. And because only the surgeon and even veterinarians are able to observe living matter. Only.
Yeah.
So they have to participate to this kind of research to find new things, I am just at the beginning. I am just beginning but I am sure that in 200 years, we will see living matter in a different way.
Yes.
And
Thanks.
of course, human in the nature.
Yeah. Thanks for opening the post-Vesalian aura, Jean-Claude. It's an honor. Thank you for this interview. It's been a long time now.
I can speak at
For
least
one more
6
hour.
hours, 6 hours more.
No, but I think it was perfect. Thank you
Okay.
so much for participating.
Thank you, Bruno.
Love you. Lots of good health for you. Hopefully, I
You
come back
too.
to Bordeaux one day. And
Yes,
yeah,
yes. You are always welcome.
thank you. Jean-Claude, blessings.